deep into that, but we're going to use that for some particular game applications. All right. We spoke about a few solution concepts so far. I stopped the previous lecture, if you did look at the slides for the right before extensive form games, and I don't want to repeat that again because you all heard that last semester. So that's part of the material of this course as well. We will touch on extensive form games a bit more deeper, a little more deep than we did so far, but the basic definitions that we had, I would assume that you know them. All right, and one thing that I hope you remember about extensive form games, that they always possess, in fact, subgame perfect equilibrium, which is a subclass of pure strategy Nash equilibria. So those games always have an equilibrium in pure strategies, which is not necessarily true for general games. Right? And that's why we know that every extensive form games we can represent in a normal form, but not the other way around. If we have a game in a normal form, not always there is an extensive form game with perfect information that would be equivalent to that game. Right? So extensive form games are a subclass of general games that we usually deal with. And they have Nash equilibrium pure structures. Today we will talk about another class that has many applications in multi-agent systems. And those games also would possess Nash equilibrium pure structures. So why pure strategy Nash equilibria are important to have? Because in many situations where you have single shot games, not repeated games, it actually does not make physical sense to apply a mixed strategy. Because the strategy that the agents would play in real life, in practice, would be pure. And you are interested in having some stable state of your system, right? So that's why pure strategy Nash equilibria are of interest, and we know that they do not necessarily exist in all the games. So it's interesting indeed to find those classes that would have, real-life applications, and for which we can conclude that they have Nash equilibrium pure structures. So if we have a situation that this model describes, we would also know that there is a stable state. So that would be great to have. So we would like to identify those classes, and one of them, which is one of the central ones in multi-agent system, the model comes from transportation problems, but then it has become very popular in in multi-agent systems due to other applications that can be modeled as traffic on roads, and those are congestion gates. The word congestion here does not necessarily have a negative connotation. Congestion just means, literally, load on the resources we're going to use. Congestion may be good or bad for you. When is it bad? Well, if you indeed think about traveling on roads, then the more congestion you have, the slower you go, so that has a negative impact. If you think about building something together and having hosts that you can share, then the more agents you can share this cost with, the better for you, right? So congestion can be good or bad, depending on the context of the game, right? So don't take it as only negative. So what is the setting? We have a set of players, and each one of them has to choose from some finite set of resources that they will share between them. So a player chooses some subset from a given set of resources. Then the utility or a cost, once again, depending on the context of the game, from each resource that our agent uses would depend on the total congestion on that resource. Okay, so I've chosen my resources, some other agents have chosen their resources, some of them we share, so there are X, I agents on resource I, and the cost or utility that each of us who uses that resource have from that resource would be a function of our total number of users. Now, my personal utility or cost in the game would be just the linear sum of those utilities or costs from all the resources that I do use. Okay? So we see congestion literally on roads. We see those models in many other domains. You can think about routing problems. What are the resources here that I use? Different routes that I can choose. Okay, I can go from, I don't know, that's a map, map of London. From Finchley Road, I want to get to Piccadilly Circus. I have two possible routes. I can take Jubilee Line or Metropolitan Line to Baker Street, then change to Bakerloo and get off, or I can take Jubilee Line and go to Green Park and then change to Piccadilly, right? So there are different routes that we can choose from, and let's assume that we want to minimize the time of travel, or then there can be other considerations, right? So routing problems, or routing in computer networks. When we send messages, the messages can take different routes in the network from one point to another. There are also other applications such as, for example, factory production. We may have different firms that produce identical products, and a buyer can choose who to buy from, right? Or there are services and so on. So there is a competition between the firms for buyers, right? Then there are cost-sharing models. You can look at two servers that need to, like we want to connect between two servers. We need to build a link, and then everyone who actually is going to use that link, we can share this cost with. Another situation, we may have some agents, either people or robots, that have to complete a given set of tasks, and we can allocate the agents to the tasks so that we have several agents sharing the same task, and then the time by which we complete the task would depend on how many agents we have allocated there. So these are all different stories that fall into the same model, in fact, right? Resources shared by agents, right? And then the congestion on each resource may have a negative or a positive impact. So formally, we have a game that is defined by the following components. We have a set of agents, a finite set. We have a set of resources, also a finite set. And the set of pure strategies for each of the agents would be some subset, not a subset, a collection of subsets of the given set of resources, right? So it's a subset of the power set of the set of resources, right? So it doesn't have to be the complete power set. It may be just a subset, just some sub-collection of those. The thing that you can think about is you may have, if you think about the routing problem, and you have different agents that each one of them has their particular source and their particular destination, and you can think about segments of the road as individual primary resources, then a subset of such resources would constitute a path in the network, right? And a given agent would only consider those paths that go from his source to his destination. Okay, so it doesn't have to be the same for all. Okay, so it's just some sub-collection of subsets of the resources. As before, the combination of strategy spaces would give us the set of strategy profiles. Now, given a particular choice of strategies for the agents, for each resource we can associate, with the congestion of that resource, which is just the number of players that have chosen that resource in their given strategy. Okay? That would give us a congestion vector. The size of the vector as the number of resources, right? For each resource, how many users does it have? Now, for each resource, we define a utility, would be a cost function, that is just a function of the number of users of that resource, right? And there are no assumptions in the general model about the behavior of that function. It is not assumed to be monotonically increasing, monotonically decreasing, or monotone at all. Okay? So it can have any behavior. We will consider later particular cases where this function is well behaved, so that we can say something positive about that. But so far, no assumptions at all. Okay? And now the payoff for a player would be the sum of those utilities given the congestion on the resources under a given combination of strategies from the resources that that agent uses, right? So we look at the resources in the strategy of agent I, and we take the utility of those resources given the congestion on those resources under the strategy profile that we have. Questions so far? There is one special case of those games which make things way more simple. It's called, it has actually many names. One of them is resource selection game. Another is singleton congestion games. The third one is symbol congestion games. They all mean the same thing. There, the strategies for the players are single resources. Okay, so instead of having subsets, I only choose single resources. So that's a simple special case of that. And then the utility would be the sum of utilities, actually not the sum of utilities, just the utility from one resource that I use. Let us maybe have some simple example so that we see how things work. So assume that I have three resources, R1, R2, R3, and I have, how many do you want? 8 agents. No, that's 2. Now, for each of the resources, I have now to define the game, I have to specify the utility of each one of them, right, for any possible given congestion. How many possible values of congestion can we have? 1, 2, 3, 4, or 5, depending on how many users we have. If there are 0 users, we actually do not need, like, we may have a convention that the utility will be 0, but in fact, we don't need to define that value because it will not appear in the utility function of any of the users. Right? If I use that resource, there is already a congestion of at least 1. Right? So we need to define these, and so on for each of them. Okay, let us do it. I don't know. If I'm alone, then I can enjoy that 10. If there are 2 of us, the utility drops to 5. And if there are 3 or 4, 5, then the utility is just 1. Here you can see that the way I define this function, that's monotonically decreasing with congestion, so congestion has a negative impact. So in such a situation, what would the agents like to assume that, you know, we have the same function for all the resources? I just don't want to make it too long. R, maybe R1 or R2 or R3. But generally, there can be different functions for all the resources. So the function may be different for the resources, but it depends on the congestion of the resource, not on the identities of the agents that use it. And it's the same for every user of that resource. Okay? So the game, the model is homogeneous towards the players. Okay? So in this situation, what would you expect from the agents to do? How do you think the Nash equilibrium in this game would look like?
Choose different resources.
Yeah, then we try to somehow spread themselves evenly among the resources. Okay, there are 5 of them, so we would have 2 to 1, and there is no incentive to each of them to deviate. Right? This guy, anyone from here, if they deviate to the resource with congestion 2, they will only decrease their utility. Deviating to resource R3 will not make a change. This guy doesn't want to deviate because there will be an increase in his decrease in his utility. So that's an example. Now, okay. The good news about this model is there are always pure strategy Nash equilibrium in this game, which is pretty good. In fact, we will say even more positive things about that, but let's look at how it was proven. I'm not going to give you the full proof, but just the idea. How it was proven when the model actually was just defined. It was in '73. So the paper that defined the model and proved that it has a pure strategy Nash equilibrium, and also showed a couple of application examples. I think it has 2 or 3 pages including references. It's very short. So yeah, the proof is simple. So for every strategy profile and for every player, we define a variable, a binary variable that takes values either 0 or 1 for each of the strategies of the agents. If he chooses that strategy in the given profile, it will be 1. If he does not, it will be 0. So just an indicator. Okay. And then, using those variables, Rosenthal, the author of the paper, he defined this optimization program that maximizes some function. We will get to that function in a second, under some constraints. What are the constraints? The first constraint, the sum of x's for each agent is 1. What does it mean? You choose exactly one strategy. That's all it says. Okay? Every agent chooses exactly one strategy. The next constraint actually defines the congestion on each of the resources. So it takes the summation of these binary variables for all the resources that an agent uses, and also over all the agents, right? So for each resource, it will indicate exactly how many users there are, how many players have chosen that particular resource. Okay? So that just defines the congestion vector. And now this value appears in the objective function. What is the objective function? The objective function does not have practical meaning. Literally, this is the accumulative sum, accumulative congestion, not real congestion. So, well, utility. You look at the utility on each resource. So the summation is over all resources, but for each resource, you don't take the utility under given congestion. You take the cumulative sum of those utilities from congestion at 0, 1, 2, so on up to the congestion that it really has under the given profile. Okay? So that's a sum, the total sum of cumulative utilities on each resource. It does not have a practical meaning indeed. It doesn't indicate anything. It's not the social welfare of the system, it's not the sum of utilities of the players, that's something more, but that's what it is. And he has shown that this system always has a solution, and the optimal solution to the system actually corresponds to this Rajanesh magic. Okay, so we optimize, we will see why this magic works in a few slides. So we take some function, we write the constraints that actually define that this is a feasible, strategy to choose, no more than that, okay? And optimizing that function brings us to this Rajanesh equilibrium. Why is that true? So this function, this magic function that Rosenthal just guessed, it was explained 20 years after, 23. That function actually has very particular meaning in the game. And it's called the potential function. The term does come from physics. Okay, so that's the intuition behind this potential function is exactly the same as in physics. Okay? So we define a function onto the space of strategy profiles, okay, the combination of strategies of all the agents, and give it a real value. Okay. And the function is called the exact potential for a given game if you look at each agent, agent I, and you look at two different strategies that this agent may choose from. Any pair of strategies from his strategy set under the fixed combination of strategies for the rest of the agents, the difference in his utility between playing those two strategies should be exactly as the increment in the potential function from the same strategy profiles. Now, this is very strong condition. Why is that? because potential function does not depend on the identities of the players. You define this function for the whole strategy profile. And somehow, for every deviation, say, define the number for strategy profile, player 1 changes his strategy in that profile, the change of the potential function should be exactly as the increment in his utility. Another player changes his strategy, the increment in the function should be exactly as the change in his utility. Right? So this is a very strong requirement, and not every game would possess such a function. Okay, let's have an example. Say here, for instance, we have just 2 players and 2 strategies for each, and these are the utilities. Now, the first player changes his strategy from A to B, his utility drops by 4, so the potential function should also drop by 4. Right? So I have 5 and 1. I could have started from any number in a given fixed profile and then try to. Then from B to D, the second player changes his strategy, his utility does not change, and so the potential function must not change. So it stays 1. Now from BD to AD, the first player changes his strategy, his utility grows by 3, and so the potential function must grow by 3, so it becomes 4. And then back from D to C, the second player changes his strategy, his utility grows by 1, and so the potential function. Okay. So in this game, indeed, such a function is possible to construct. Right? If now, for instance, here, instead of 8, I had 5, that would not be possible to construct such a function, right? Because, let's say, we had all the inequalities over there, and now the function has to drop, but it grows given the other. So not every game would have that. Why having such a function is a good thing? Because if the game is finite, this function would always have extreme points, global and also local, minimum or maximum, right? Maximum, for instance, in this case. In every local maximum of this function, what happens? The function cannot grow in the given, neighborhood. The function cannot grow, but we know that when function grows, there is a player that can increase his utility. If the function cannot grow, means that none of the agents can increase their utility by deviating from the given strategy. What does it mean? That's a Nash equilibrium. Okay? So every local maximum of the potential function is a Nash equilibrium of the game. So if you have this function, you have an equilibrium with your strategies. But now actually you can notice that the requirement of the exact equality, the equality between the increment in the utility and the potential function is actually too strong to conclude the existence of a Nash equilibrium. Like, as long as this grows and that grows, that also would work exactly the same way. The local maximum would mean no increase in the utility of any player is possible. Right? So it doesn't have to be exactly the same increment. So we may relax a little bit the definition, and that would be called an ordinal potential. Pretty much the same thing, except of as long as the increment in the utility is positive, so that the change in the potential function is positive, and the other way around. Right? I've changed slightly the example. These are the same utilities in the game, but the function is different. It's 3. It has to drop by 4, but yeah, for now it just has to drop. So it drops by 2, not by 4, whatever. No change here, no change here. Grows, grows. And again, local maximum would define an Nash equilibrium. Is it too strong again? Yeah.
So the potential values are just correct for this scenario, moving from BC clockwise, because if we start from AC, for example, we will have different values.
Well, you may define actually infinitely many potential functions. If you can define one, you can define infinitely many. Any affine, move of that function would also be a potential function. You also have to satisfy the condition, the same direction of the inequality. In this case, for exact potential, also the same increment. But if in the previous example, I started with, I don't know, I started with this profile, but put 10 here. Then what? 10 must drop by 4, will be 6, 6, 9, 10. Also a potential function. Okay? So, as long as there's one, there are infinitely many. But this one is different from the previous case because the value of the change is not exactly as the change in the utility function. Here we only care about the same direction of the inequality. Okay? There I wanted, in this case, to drop it exactly by 4 as the utility, but for ordinal potential, it's enough that it drops. Doesn't matter by how much. So here the condition is if and only if. Positive there must be positive there and the other way around. Which then said that if there is no change in the utility function, there must be no change in the potential function as well. But that's again too strong if we're after just existence of a Nash equilibrium. Because what do we need? When we stop at the potential function, no change in the potential function does not grow. The only thing that we have to satisfy at that point, that means that it's impossible that there is an agent whose utility grows around there. So that's enough to have only this direction of this condition. As long as there is someone whose utility grows from x to y, the potential function must grow as well. The other way around, we don't care. Right? So in the same example, for instance, when there is no change in the utility of this player here, the potential still could change in any direction, by the way. Okay. But then if I know that if the function has stopped, then there is no change in the utility of the players from that point. Okay. So this is a maximum of this function in this game, and indeed there is a Nash equilibrium. Right? The function drops if the first player changes his strategy, his utility drops, so he wouldn't do that. The function drops in that direction, the utility of the second player drops, so he wouldn't do that either. Nash equilibrium indeed. Okay, so that's enough to have what is called the weakest notion of potential, generalized ordinal potential. So there are 3 levels of potential functions, but the weakest is enough for the existence of a two-strategy Nash equilibrium. And in fact, that's a full characterization. Now, what we said now is a little bit more than just having a two-strategy Nash. It actually says that if we start from any profile and let the agents one by one, in any order, improve their strategies. Okay? Just, we play a game, I ask all the agents, is there anyone who wants to change their strategy? Yeah, I do. Please do that. Next, 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 next. If we apply such a path in strategy profiles, so the definition of a path is that's a sequence of profiles, so that at each step there is exactly one agent who changes their strategy. Okay? And we would say that such a path is an improvement path is if every such a change actually is an improving move for the given agent who makes the move, right? So the agent who makes the move at step K, at that step increases his utility. Okay, so we can talk about paths, improvement paths. And then if we have a potential function, even if just a generalized ordinal potential function in the game, as long as we go along such an improvement path, we increase the potential function. Right? Because someone increases their utility, that means that at every such step, the potential function grows. And then we know that because the game is finite, we will reach some local maximum. There will be a Nash equilibrium. So not just we have a Nash equilibrium in this game. We have what is called the finite improvement property, saying that doesn't matter in which profile you start, doesn't matter in which order you let the agents to improve their strategies one by one, you will find a Nash equilibrium eventually. Okay? That's way more strong than just having one. So actually you can just let the agents play almost freely. Okay? The only rule you get, act one by one. That's it. There could be other dynamics in the game. So we said that if every agent just improves, doesn't matter how much their utility, then may make a move that would define just an improvement path. You may expect from the agents to make maximal improvements, best possible improvements of all the improvements that you have at every step. That would define a dynamics which is called best response dynamic. This is just a special case of all improvement dynamics. So if you have FIP, finite improvement property, you will have convergence also of best response dynamic. That's a weaker requirement. Sometimes you may have this, but not that. Okay, you may have cycles in better responses, but you will have best response dynamic acyclic. And another even weaker property, it's called weaker cyclicity, saying the following thing. Best response dynamics or better response dynamics may cycle, but there exists some improvement path that converges from every given profile. Okay. That is still stronger than just existence of a Nash equilibrium, but here you would need to find a particular path that leads to it. Okay. And we will see example of such things. Now, how hard computationally is that to find a Nash equilibrium? So we said, well, that's very easy. You just give the players do what they want myopically. They only consider, the given state and see if they have an improvement from that state. That's a very simple dynamic. And we know it converges if the game has a potential. In congestion games, there is always a potential function. All good. But eventually it will converge, not necessarily in polynomial time, and in fact the complexity of finding a Nash equilibrium is what is called polynomial time local search. That's intuitively the same as to find a local maximum of a function. Okay. I'm moving on to something. Shall we have a break or not? Up to you. Yeah, let's have a break.